Hi, this is Ms. Wiles, and today we're looking at Common Core Standard F1 IF5. Y'all don't really care what that means, but what you're going to be doing is explaining how the domain of a function is represented in a graph. You're going to be able to state appropriate domains and ranges of a particular function based on the context of the problem. And let's look at how we'll do that. Now, here's an example. A rocket is launched from 180 feet above the ground at time t equals 0. The function that models this situation is given by h of t equals negative 16t squared. That should be a squared. Change that to a squared. Negative 16t squared plus 96t plus 180, where t is measured in seconds and h is height above the ground measured in feet. So somebody with a lot of time, some engineer, decided or found out that here's this function that it models what happens when they launch a rocket. When they launch this rocket from the ground, well, actually it was already 180 feet above the ground, and when they launch it, time is 0. And as time passes, what happens to that function? What happens to the rocket as time passes and they have launched that rocket? We have an X and a Y. X measures time, and Y measures the height of the rocket. Now, in this case, does it make any sense for X to be negative? No, because we don't have a TARDIS. We are not time travelers. X is not going to be negative. So this X has to be positive because we start with 0 time when we're talking about launching a rocket. Now, at 0 time, when we begin, the rocket is already at 180 feet. It's already sitting at 180 feet. And if we look at the construction of the function, we see the plus 180 at the end, telling us that when we start, the rocket is already at 180 feet. Now, when they launch it, unless something terrible happens, the rocket is going to go up. And then what's going to happen? It's going to come down. Eventually, it's going to come down. So we have to look at what's a reasonable domain for the function. And when we look at that, we find out where this function is going to end. Let's pause here for a minute. Domain is our x values. Domain are x values. What would it make sense for x to be? Since x, or t in this case, since we're using t to represent x, since x in this case is t and that is time, it's reasonable to expect that time would be measured from 0 on up. That's your domain, what is reasonable. And it would not be reasonable for it to be all real numbers because it's not reasonable to think that time is negative. So we don't have that negative time. This example goes a little bit farther than we need to right now because of the fact that this is a quadratic function. It goes a little bit farther than we need to right now, so I'm going to hold on to that. We're going to stick a pin in it, as we would say, and then come back to it. Because it's the idea of that domain and what it would mean. Now, the range are the y values. Now, the one thing that we hope, when in this situation, we hope the rocket doesn't come back down and go into the ground. We expect that it's reasonable that the rocket will stop at ground 0, that it will land on the ground, that it will not go down under the ground. So our range, it is reasonable to expect that we want our range to go from 0 up to the top where that, the top point where that rocket goes. So our range and our domain are not all real numbers. They're the ones that fit the context of the problem. Let's move on from this problem. Here's an example of something that's more reasonable for us to do. The domain, we're going to fill this in, is the set of all possible values of x in a function. The range is the set of all possible values of y in a function, in a particular function. Not just in every function, but in a particular function. Let's look at these different functions that we have here and find the range and the domain of these. Now, number one, we're looking at a function that is f of x equals 4x plus 12. What is it reasonable for x to be? Well, if you say anything, x could be anything, then we denote that or show that by saying that the domain is all real numbers. All real numbers. We can also denote it by saying that it's from negative infinity to positive infinity. If there aren't any numbers that I could put in that function and wouldn't get some kind of output. And for the range, you look at that, we would expect to get anything, almost anything out of that. Because it's going to be a line that goes in infinity direction both ways. So our range is the same. It's all real numbers. It goes from negative infinity to positive infinity. We're not asking what they are, but what set of numbers is reasonable for us to expect those values to come from. Next problem. Joe had a summer job that pays $7 an hour, and he worked between 15 and 35 hours every week. His weekly salary can be modeled by the equation S equals 7H, where S is his weekly salary, and H is the number of hours he worked in a week. Now, here's where we have to do some understanding of how this function, how this situation turns into a function. And what we have this equation, S equals 7H. Now, H is the same thing as X. And H is the same thing as X, and S is the same thing as Y, or f of X. So we look at those and we ask ourselves, in this situation, what does it make sense for H to be? Because H is our domain. H is our domain, and if we look at the problem, H is the number of hours he worked in a week. That's what it tells us. And it also tells us in the problem what that number is. The number of hours that he works during the week is between 15 and 35. Now, the way that we can show that is to say that H can be between 15 and 35. That little inequality that you see right there, that grouped inequality, means that the value in the middle, this H, can be between 13 and 15. It's less than or equal to 35, and it's greater than or equal to 15. So it's somewhere in between those numbers. So we can show that domain with an inequality, or we can show that domain as in set notation. In set notation for this domain, we would put a bracket and a 15 to show that our domain could be 15. It can go as low as 15 or as high as 35. If it can include those values, we put these blocks. We put a blocked parentheses or a blocked grouping symbol instead of the parentheses that we put here to show that it just goes on and on, or that it doesn't include, there's no end value that it includes. The domain is based on the situation. The range is also based on the situation here. The range in this situation is found by using the formula S equals 7 times H. As S is his salary, and that's the Y values, but it won't go down. He's going to make some money. He can't make negative infinity money. He's not going to make zero money unless he gets fired. As long as he works 15 to 35 hours a week, he's going to make some money. And since he's making $7 an hour, we can find the minimum that he's going to make by doing the minimum that he will make is 7 times 15. So the minimum that he can make, being 7 times 15, is 105. That's the minimum amount of money that he can make. The maximum money that he can make is 7 times what?
35.
35. And 7 times 35 is 245. Noah's my calculator man. He's checking it, making sure that I'm staying straight because I'm doing it here. So the maximum that he can make is 245. So our range, S, is between those two numbers. He could make 105, as little as 105, and he could make as much as 245. Or we can show it in set notation as 105 to 245. And see, the idea is that he could, in the domain, he might not work exactly 15 hours. He might work 15.25 because maybe there's a time clock and he just punches out. He might work 17 and a half hours. And if that happens, he's going to make some money somewhere in between these two values. So that's how that domain is going to work. Let's look at the third example. The third example, we have a ball that was thrown into the air, similarly to the rocket that was 180 feet off the ground. This ball was thrown into the air with an initial velocity of 72 feet per second. The height of the ball after t seconds is represented by the equation h equals 72t minus 16t squared. Notice there's a lot of t squareds and t's in these equations about time, what happens over time. The graph of the function is shown to the right. With the graph of the function, we can tell some things. Where was the ball when he let loose of it? But what does that represent? The ground. He actually had the ball on the ground. I don't know, he had his hand under it or something. He built something, but that ball was right here on the ground when it was thrown into the air. And it was thrown into the air, and how high did it go?
72 feet.
It went about 82 feet. Read it here. It went about 82 feet. This is velocity. This is how fast it's going. It's going 72 feet per second. So from that, you can tell how much the initial velocity, what's going to happen when gravity starts pulling on that initial velocity. It's going to slow down a little bit. And that's why the ball doesn't go straight up into the air. Because gravity starts pulling on it and slows it down. And it slows it down, and that's why it takes that long for it to get up here to 82 feet. And then what happens? It starts coming back down to the ground. Now, when it comes back down to the ground, it lands on the ground. It doesn't go into the ground. So what would our domain be? From 0 to what? Domain, what's domain about? Domain is about x. Domain is here. Your domain is on your x. It's all about the x. From 0 to 4.5. That's what that time is in between, from 0 to 4.5, because domain is about the x value. We could also show that by saying, look, we need to use those brackets because it actually includes the 0 and the 4.5. And what is the range based on, x or y? The range is based on y. So our range is based on this. How low is it going to start? At 0. And how high is it going to go? By 82. And what do we call that? H, because that's the height. And that height is going to be at some point anywhere between 0 and 82 feet. So we would also be able to show it like that. And that's all I have to say about that.